Have you ever had that dream? The one where you're standing perfectly still, but the ground beneath you begins to move. Not an earthquake, not a landslide, but a slow, inexorable drift. You look down and see the cracks appearing, not in the soil, but in reality itself. You are moving, and you have always been moving. You just never felt it until now. I have that dream often, because I know it's not a dream, it's the truth. We are all trapped in an illusion of stillness. The ground beneath your feet feels solid, permanent. The chair you're sitting in, stable. The horizon, a constant line. We built our lives, our civilizations, our very understanding of reality on this foundation of stability. But it is a beautiful, necessary lie. The truth is, you are currently riding a cosmic bullet train through the void. You are spinning, falling, and soaring at speeds so immense they defy human intuition. And you are not alone. Everything, every dust mote, every planet, every star, every galaxies caught in the same grand, chaotic, and breathtaking flow. Where is it all going? Is there a destination, a final cosmic port where this unimaginable journey ends? Or are we simply adrift in an infinite, expanding sea, destined to fade into silence? This is not just a story about astronomy. This is a story about our home, our journey, and our ultimate fate. This is the story of the greatest motion ever conceived, and it starts with the shattering of a perfect, still, and comforting lie. Look up at the night sky. What do you see? For countless generations, our ancestors saw the same thing, a fixed, immutable tapestry. The constellations Orion, Ursa Major, the Southern Cross were eternal. They were the unwavering landmarks of the cosmos. The moon followed its predictable, smooth path. The planets, the wanderers, may have meandered, but they always returned. To the human eye, it was a clockwork universe, elegant, divine, and, above all, still. This perception was our bedrock. We, naturally, placed ourselves at the center of it all. The earth was the solid, unmoving stage. The heavens were the rotating backdrop. This idea, the geocentric model, wasn't born out of arrogance, but out of simple, straightforward observation. It worked. It predicted the seasons. It explained the sunrises and sunsets. It gave us a place of supreme importance in the grand scheme of things. It was comforting, but comfort is not a reliable guide to truth. The first crack in this celestial facade appeared not with a bang, but with a whisper, a mathematical whisper. In the 16th century, a Polish cleric and mathematician named Nicolaus Copernicus, armed with little more than his own intellect and a deep-seated belief in the elegance of mathematics, dared to suggest the unthinkable. What if we are not the center? His model was radical, heretical, and for its time, utterly terrifying. He proposed that the sun, not the earth, was the center of our local universe, that our world was just another planet spinning on its axis and orbiting a central fire. He gave Earth 3 motions: a daily rotation, a yearly revolution, and a slow, wobbling precession. We were, for the first time, set adrift. But Copernicus was a cautious man. He held on to his work for decades, only publishing his masterpiece on the revolutions of the heavenly spheres on his deathbed. He knew the fire he was playing with. His model was elegant, but it wasn't perfect. He clung to the ancient Greek idea of perfect circular motion, forcing his planets into circles, which required complex loops and epicycles that made his predictions barely more accurate than the old Earth-centered system. The crack was there, but the dam was still holding. Then an Italian physicist and astronomer named Galileo Galilei pointed a new invention, the telescope, at the heavens, and the dam burst. Imagine the sheer, heart-stopping thrill Galileo must have felt. He wasn't just reading equations on a page. He was seeing. When he looked at the moon, he saw a world. It wasn't a perfect, smooth celestial orb. It had mountains, valleys, and craters. It was a landscape, a place. It looked disconcertingly like Earth. Then he turned his telescope to Jupiter, and he saw them, 4 small, bright stars, lined up neatly, dancing around the giant planet. Night after night, he tracked them. They changed position, but they never left Jupiter's side. They were moons, moons orbiting another world. This was the kill shot to the old cosmology. If everything had to orbit the Earth, what were these for rebels doing, circling Jupiter? They weren't. The Earth was not the universal anchor of all motion. But Galileo saved his most elegant proof for Venus. He watched as Venus went through phases. Just like our moon, it grew from a thin crescent to a full glowing disk. In the Earth-centered model, this was impossible. If Venus orbited Earth, its illuminated face would always be pointed mostly at us. But the full set of phases could only be explained if Venus was orbiting the Sun, and we were watching from another moving platform, a platform that was also orbiting the Sun. The data was in. The verdict was clear. We were in motion, yet the question remained, how do we move? What are the rules of this grand dance? Copernicus had the vision. Galileo had the evidence. But it fell to a reclusive, deeply religious German mathematician named Johannes Kepler to provide the choreography. Kepler was a mystic and a mathematician, a man who believed the universe was built on geometric harmony. He became the assistant to Tycho Brahe, the last great naked-eye astronomer, a man who had compiled the most precise and extensive records of planetary motion ever known. When Tycho died, Kepler inherited this priceless treasure trove of data. He focused on Mars, the red wanderer that had always been a nuisance to astronomers. For years, Kepler tried to force Mars's path into a circular orbit. He failed over and over again. The data refused to cooperate. Mars was stubborn. It didn't follow the perfect, divine circles that philosophy demanded. So, in a moment of brilliant, humble insight, Kepler did something revolutionary. He abandoned 2,000 years of dogma. He let the data lead him. And the data led him to a shape the Greeks had considered imperfect, an off-kilter circle, the ellipse. This was Kepler's first law. Planets move in elliptical orbits, with the Sun at one focus. But that was just the beginning. He noticed that planets don't move at a constant speed. They speed up when they are closer to the Sun and slow down when they are farther away. This became his second law. A line joining a planet to the Sun sweeps out equal areas in equal times. Imagine a cosmic triangle connecting the Sun, a planet's position today, and its position a week from now. The area of that triangle will always be the same, regardless of where the planet is in its orbit. To make the area equal, the planet has to move faster on the short, tight part of the triangle near the Sun, and slower on the long, stretched part. Finally, he found the harmony he was searching for. His third law, the law of harmonies. established a precise mathematical relationship between a planet's distance from the sun and the time it takes to orbit. The farther a planet is, the longer its year, and it's a predictable, beautiful ratio. The solar system suddenly made sense. It was not a system of perfect circles, but of elegant ellipses governed by precise, universal mathematics. The illusion was shattered. We were not still. We were a planet orbiting a star. The question of are we moving was definitively answered, yes. But a new, even more profound question immediately took its place. A question that would haunt scientists for the next century. Why? Why do the planets orbit the sun? What invisible hand guides them along these elliptical paths? What force keeps them from flying off into the void or crashing into the sun? The answer, as the story goes, fell from a tree. Isaac Newton. The name itself carries the weight of a fundamental shift. While hiding from the plague in the English countryside in 1666, he saw an apple fall. It was a mundane event witnessed by countless people before him. But Newton saw something else. He saw a force. He asked a simple, childlike question with cosmic implications. If the apple falls, does the moon also fall? The answer, he realized, was yes. The moon is constantly falling towards Earth, but it is also moving sideways so quickly that it keeps missing the ground. It is in a perpetual, graceful state of free fall around the planet. The same force that pulls the apple from the tree pulls the moon towards Earth, bending its path into a curved orbit. This was gravity, not just an earthly force, but a universal force. Newton formulated his law of universal gravitation. Every particle of matter in the universe, every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In simpler terms, everything pulls on everything else. The sun pulls on Earth. Earth pulls on the sun. Jupiter pulls on Mars. And yes, the apple pulls on the Earth, just as the Earth pulls on the apple. With this single, breathtakingly powerful idea, Newton unified the heavens and the earth. The same laws that governed a falling apple governed the orbit of the moon, the planets, and the stars. He gave us the mathematics to calculate it all. He could now explain why we move. He could calculate our speed. Using his new laws, it became possible to determine just how fast this cosmic bullet train was traveling. We orbit the sun at a staggering 107,000 kilometers per hour. That's nearly 30 kilometers every single second. Fast enough to circle the Earth at the equator in just over 7 minutes. Mercury, closer to the sun and feeling a stronger gravitational pull, moves even faster at about 47 kilometers per second. Mars, farther out, moves more sedately. It all fit. Newton's clockwork universe was elegant, predictable, and complete. Or so it seemed. For the first time, we understood our locomotion. We were on a planet, spinning and orbiting a star, held in place by an invisible mathematical force. The journey had a description, but a description is not a destination. We had solved the puzzle of our solar system, only to look up and realize this was just the first tiny room in a cosmic mansion of unimaginable size. And we were about to discover that our entire solar system, our sun, the anchor of our existence, was itself not still. It, too, was moving, but where? With the motions of Earth settled, astronomers turned their telescopes and their minds to the stars. The fixed stars? Were they truly fixed, or were they, like us, adrift? The first clue came from an unlikely source, a musician. William Herschel was a German-born composer who settled in England. His passion, however, was not for music, but for the stars. He became obsessed with building telescopes, grinding and polishing his own mirrors until they were the finest in the world. With his sister, Caroline, as his dedicated assistant, he embarked on an ambitious project to map the structure of the universe. His method was simple but grueling. He would point his telescope at a patch of sky and count the stars. He would then move his telescope slightly and count again. Night after night, he and Caroline compiled a vast census of the heavens. What he found was a pattern. The stars were not scattered randomly. In some directions, the sky was thick with them. In others, they were sparse. The greatest concentration of stars lay in a broad, faint band that arched across the sky, the Milky Way. Herschel concluded, correctly, that we were inside a vast, flattened disk of stars. He called it the grindstone universe. He even placed the sun near its center. He was wrong about the details. He didn't know about interstellar dust that blocked his view, making the universe seem much smaller than it is. But his fundamental insight was revolutionary. The sun was not floating in an infinite, random void. It was part of a system, a structure, a galaxy. If we were inside a structure, then perhaps we had a location within it. And if we had a location, then perhaps we were moving through it. Proving this was a monumental challenge. How do you measure the motion of a star? They are so impossibly far away that any movement, any proper motion, as it's called, is infinitesimally small. It's like trying to measure the movement of a ship on the horizon, using only your naked eye from 1,000 miles away. It required patience, precision, and a new level of astronomical technique. The man who finally pinned down the sun's motion was a quiet, meticulous Dutch astronomer named Jacobus Kapteyn. In the early 20th century, Kapteyn undertook a project even more ambitious than Herschel's. He gathered star catalogs from observatories around the world, compiling the positions and motions of thousands upon thousands of stars. He was looking for a pattern, a drift, and he found one. The stars weren't moving randomly. They seemed to be streaming in two great currents. At first, it looked as if the stars themselves were divided into two swarms. But Kapteyn, thinking deeply about frames of reference, made the intellectual leap. What if this pattern wasn't about the stars moving? What if it was about us moving? Think back to the train. If you're moving through a crowd, the people directly in front of you appear to be moving towards you, while those behind you appear to be receding. Kapteyn realized the stellar streams were exactly that, an illusion of our motion. He ran the calculations, and the stellar motions snapped into focus. The only way the data made sense was if the sun and our entire solar system was moving towards a point in the constellation Hercules at a speed of about 20 kilometers per second. The anchor was gone. The sun was not still. It was a ship sailing through the ocean of the galaxy. We had a new velocity, a new direction. We called our heading the solar apex. This was a profound demotion. First, we were not the center of the universe. Then, we were not even the center of our solar system. Now, our sun was not a fixed point in the galaxy. It was a wanderer. But Captain wasn't finished. He used this new understanding to create the first true model of our galaxy, the Captain Universe. It was a flattened disk, about 40,000 light-years across, with the sun still comfortingly near the center. He was wrong again, but his error was about to be revealed in the most dramatic way possible, by a man who would look beyond our galaxy and forever change our sense of scale. While Captain was mapping our galaxy, a great debate was raging in astronomy. What were those faint, fuzzy patches of light scattered across the sky, the spiral nebulae? Were they just clouds of gas within our own Milky Way? Or were they something else? Entire island universes, other galaxies far beyond our own. The debate was settled in 1923 by an American astronomer named Edwin Hubble, using the most powerful telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson. He focused on the Great Nebula in Andromeda. He was searching for a special kind of star, a Cepheid variable. These stars have a magical property. They pulsate with a regular rhythm, and the period of their pulsation is directly related to their true, intrinsic brightness. Discovered by Henrietta Swan Leavitt, this period luminosity relationship was a cosmic yardstick. If you could find a Cepheid, measure its pulse, you could know how bright it truly was, by comparing its true brightness to how dim it appeared from Earth. You could calculate its distance with stunning accuracy. Hubble found his Cepheid in Andromeda. He measured its pulse. He calculated its distance. The number was staggering. Andromeda was nearly 1 million light-years away. We now know it's 2.5 million. It was far, far beyond the outermost borders of Captain's model of the Milky Way. Andromeda was not part of our galaxy. It was a galaxy in its own right. In a single observation, the universe exploded in size. The Milky Way was not the universe. It was one galaxy among countless others. We had gone from a single city to an entire continent, and now we realized we were just one city on a planet filled with cities. Hubble didn't stop there. He began to classify these galaxies, and, in an even more shocking discovery, he found that almost all of them were moving away from us. And the farther away they were, the faster they were receding. The universe itself was expanding. This was the second great shattering. First, we lost our central place. Now, we lost our static universe. The very fabric of space was stretching, carrying the galaxies along with it like raisins in a rising loaf of raisin bread. We had discovered a new kind of motion, a motion not through space, but of space itself. But for me, this is where the story becomes personal and where the central mystery of our journey deepens. Because this expansion, it isn't the whole story. We are not just passively riding the expanding universe. We are also being pulled, tugged, drawn by something immense and hidden. Hubble gave us our cosmic velocity, but he also revealed an anomaly. When he looked at the light from the Andromeda galaxy, it wasn't redshifted, it was blue-shifted, while almost every other galaxy was flying away from us. Andromeda was coming toward us. This wasn't just a slight drift. Modern measurements, using space telescopes like Hubble and Gaia, combined with ultra-precise radio telescopes, have given us a stunningly detailed 3D map of its trajectory. Andromeda is not just meandering in our general direction. It is on a direct collision course with the Milky Way. Right now, we are racing toward each other. Andromeda is moving towards us at about 110 kilometers per second. Our Milky Way is moving towards Andromeda at nearly 300 kilometers per second. When you account for the motion of our entire local group of galaxies, the gap between us is closing at a combined speed of over 400,000 kilometers per hour. The collision is inevitable. In about 4 to 5 billion years, our two galaxies will meet and begin a slow, billion-year-long gravitational dance, eventually merging into a single, giant elliptical galaxy that astronomers have already named Milk Drome Day. So we have a destination, a violent, beautiful, and transformative one. But is it our final destination? Is this great galactic merger the end of our journey? No, it is merely a local event, a side street on an unimaginably vast cosmic map. Because when you zoom out, far beyond the local group, you see that the collision with Andromeda is just a small, minor adjustment in a much larger, much faster, and much more mysterious flow, our entire galaxy, along with Andromeda and all our neighboring galaxies, are not just expanding with the universe. We are all moving in concert, sideways. We are being pulled, as if by a cosmic river, towards a specific point in the sky, a region obscured by the stars and dust of our own Milky Way. Astronomers, measuring the peculiar velocities of thousands of galaxies, have mapped this flow. They call the source of this pull the Great Attractor, a gravitational anomaly so powerful it is bending the paths of galaxies across hundreds of millions of light years. We are moving towards it, hundreds of kilometers per second. What is it? A massive cluster of galaxies behind the something else. We've found for decades that the Great Attractor hidden from is not view, a single lying in the zone but a dense knot of matter, a part of the supercluster of galaxies by the bulk and of even our own that galaxy may not be the end of the story. There are hints of something even larger, even more massive, pulling on the Great Attractor itself, and pulling us along with it, the Shapley supercluster. The bullet train has a trajectory. We are not drifting aimlessly. We are being guided, pulled, funneled by the gravitational landscape of the universe. We have mapped our motion from a spinning Earth to an orbiting planet, to a star sailing through a galaxy colliding with its neighbor, to an entire group of galaxies flowing towards a mysterious, hidden attractor. We have gone from thinking we were still to understanding we are moving in almost every way imaginable. But I must ask you now, at the end of this first leg of our journey, to consider a final, unsettling possibility. What if this entire cosmic flow, the spin, the orbit, the galactic drift, the pull of the Great Attractor, what if all of it is just a minor, insignificant current in a far greater, more powerful, and more terrifying cosmic ocean? We have been tracking our motion through space. But what about the motion of space itself? The expansion that Hubble discovered. What if it isn't gentle? What if it isn't constant? What if the engine driving the universe is not just expanding it, but is actively and increasingly tearing it apart? The Great Attractor pulls us. But what if there is a force, a presence, an energy in the very vacuum of space itself that is ultimately more powerful than all the gravity in the universe combined? A force that is not pulling us to a destination, but is determining the final, ultimate destination of everything. We have spent this chapter charting our path through the cosmos. But to understand where we are truly going, we must now look not at the objects in space, but at the space between them. We must confront the greatest and most mysterious discovery of modern cosmology. We must confront the phantom in the vacuum, the engine of the cosmos. We must confront dark energy, but that is a journey for the next chapter. In the silence between stars, there is a secret so profound, so utterly dominant, that it controls the ultimate fate of every galaxy, every star, every atom, and every one of us. For centuries, we believed we understood the primary force of the cosmos, gravity, the great architect, the builder of planets, the shaper of galaxies, the invisible hand that guides the cosmic dance. It is the force that pulled us from a vague sense of stillness into a concrete understanding of our motion. It spins our planet, holds our solar system together, and orchestrates the collision course with Andromeda. It is the force that now pulls our entire galaxy towards the hidden great. Gravity is the story we know, but it is not the whole story. In fact, we have recently discovered that gravity is not the master of the cosmos. It is merely a local governor, a planetary official, while a far more powerful emperor sits on the throne, dictating the destiny of the entire universe. This emperor is silent, invisible, and until the final years of the 20th century, it was completely undetected. We have given this emperor a name that speaks to our ignorance: dark energy. And its discovery did not come from seeing something, but from seeing a lack, a discrepancy, a ghost in the data that should not have been there. It was the moment we realized that the universe wasn't just expanding, it was running away from itself. This is the story of how we found the phantom in the vacuum, and how this phantom is not just moving it is reshaping reality itself. To understand the shock of dark energy, you have to go back to the late 1990s, to a scientific community that was confident it was closing in on the final chapters of cosmology. The overarching narrative of the universe seemed clear. It began with a big bang, a hot, dense genesis from which all space, time, matter, and energy erupted. For billions of years, it had been expanding, and the central question was, what would happen next? The logical answer, the one supported by everything we knew about gravity, was that the expansion was slowing down. Imagine throwing a ball straight up into the air. It rises, but the whole time, Earth's gravity is pulling on it, slowing its ascent. The universe, scientists reasoned, was that ball. All the matter and energy within it, the galaxies, and the mysterious dark matter holding them together, was acting as a gravitational brake, relentlessly tugging, trying to pull everything back together. The ultimate fate of the cosmos hinged on a simple cosmic tug-of-war, the outward momentum of the Big Bang versus the inward pull of gravity. Would the universe have enough energy to expand forever, slowing to a near halt but never quite stopping a big freeze? Or would gravity eventually win, reversing the expansion and crushing everything back into a single point-a-big crunch? This was the great debate, and to settle it, two international teams of astronomers embarked on a monumental project, led by Saul Perlmutter and separately by Brian Schmidt and Adam Rees. They set out to measure the rate of the universe's deceleration with unprecedented precision. Their tool, the death throes of stars. They needed a standard candle, an object of known, predictable brightness, so that by seeing how dim it appeared, they could calculate its exact distance. For this, they turned to a specific kind of stellar explosion, a type Ia supernova. These are no ordinary supernova. They are the thermonuclear detonations of white dwarf stars. A white dwarf is the dense, Earth-sized corpse of a star like our Sun. If it orbits a companion star and siphons off enough material to push itself over a critical mass threshold, about 1.4 times the mass of our Sun, triggers a runaway fusion reaction. The result is a cataclysm so uniform, so predictable, that these supernovae always peak at almost exactly the same intrinsic brightness. They are the perfect cosmic mile markers. The teams began a painstaking search. They scanned the heavens, looking for these brilliant flashes in distant galaxies. They measured their peak brightness, and then, using the known expansion rate of the universe, the Hubble constant, then they compared this to the distance they actually were, based on how dim the light appeared. The goal was to see how much the expansion had slowed over the billions of years it took the light to reach us. A supernova from 5 billion years ago would show a stronger deceleration signal than one from 3 billion years ago. They collected the data. They ran the calculations. They double-checked their work, and then they triple-checked it. The result made no sense. The distant supernova were too dim. They were farther away than they had any right to be. The only way this was possible was if the expansion of the universe in the past was actually slower than it is today. The universe wasn't slowing down, it was speeding up. Imagine throwing that ball into the air, and instead of slowing down, it starts flying away faster and faster, as if repelled by some anti-gravity force. That's what the data was saying. It was, as one astronomer put it, bonkers. The teams, skeptical of their own earth-shattering results, searched for errors. Was it interstellar dust dimming the light? They accounted for it. Was it some evolutionary change in the supernova themselves over billions of years? The evidence didn't support it. The conclusion was inescapable, and it was terrifying in its implications. Something was acting against gravity. A mysterious, pervasive energy was filling the vacuum of space itself, and it was causing the cosmic expansion to accelerate in 1998. They announced their findings to the world. The universe was not only expanding, but its expansion was accelerating, driven by a force we could not see or explain. For this discovery, Perlmutter-Schmidt and Rees would win the 2011 Nobel Prize in Physics. They had found the phantom, and we named it dark energy. But a name is not an explanation. What is it? The immediate question, the one that has haunted cosmologists ever since, is the simplest one. What is dark energy? The truth is, we don't know. It is the single greatest mystery in all of physics. But we have theories. The leading candidate is also the most profound and, in some ways, the most troubling. It harkens back to a concept from Albert Einstein himself. In 1917, when Einstein was applying his new theory of general relativity to the universe as a whole, he faced a problem. His equations insisted that a universe filled with matter should be either expanding or contracting. But the scientific consensus of the day, including Einstein's own belief, was that the universe was static and eternal to force his equations to describe a static universe. he introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant represented a repulsive force, a kind of anti-gravity that would perfectly balance the inward pull of matter, holding the universe in a steady state. A little over a decade later, when Edwin Hubble discovered the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder. He had missed the chance to predict one of the greatest discoveries in history. He discarded lambda, and it was largely forgotten for 70 years. Then, in 1998, it was resurrected. The cosmological constant was the perfect mathematical description for the newly discovered dark energy. It represented a constant energy density inherent to the fabric of space itself. Even in a perfect vacuum, completely empty of matter and radiation, this energy would exist. And because it's a property of space, the more space expands, the more of this energy there is, leading to a runaway acceleration. This is the current standard model of cosmology, known as the lambda-CDM model. It tells us the universe is composed of about 5% normal matter, everything we can see and touch, about 27% dark matter, the invisible glue that holds galaxies together, and a whopping 68% dark energy in the form of the cosmological constant. It fits the data beautifully, but it comes with a catastrophic problem. To understand this problem, we have to dive into the quantum world. Quantum field theory, our most successful framework for describing the subatomic realm, tells us that the vacuum of space is not empty. It is a seething, bubbling foam of virtual particles. Particle and particle pairs constantly pop into and out of existence, borrowing energy from the vacuum for an infinitesimally brief moment before annihilating each other and returning it. This quantum foam should be brimming with energy. This vacuum energy should be the cosmological constant. So we have a theoretical prediction from quantum mechanics, and we have a measured value from cosmology. They should match. They are, after all, describing the exact same thing, the energy of empty space. They do not match. The mismatch is not a small discrepancy. It is not even a large one. It is the largest and most embarrassing discrepancy in the entire history of science. The value of the vacuum energy predicted by quantum theory is 120 times larger than the value we have measured for dark energy. That's a 1 followed by 120 zeros. To put that number in perspective, it is greater than the number of atoms in the entire observable universe. If the quantum prediction were correct, the repulsive force of this vacuum energy would have been so unimaginably powerful that it would have ripped every atom, every nucleus, every fundamental particle apart in the first instance of the Big Bang. Galaxies, stars, planets, and life would have been impossible. The universe would have blown itself to bits before it even began. Somehow, the actual value of dark energy is infinitesimally, precisely tuned to the unbelievably small value that allows for our existence. It's as if a marksman fired a single bullet at a target the size of the entire observable universe and hit it dead center. This is the cosmological constant problem, and it screams that we are missing something fundamental. Either our understanding of quantum physics is profoundly incomplete, or dark energy is not a constant vacuum energy at all. Perhaps it is something else, something even stranger. What if dark energy is not constant? What if it changes over time? This idea leads us to a class of theories involving a dynamic field that permeates the universe, a modern cousin of the Higgs field. Scientists call this hypothetical field quintessence, a name taken from the ancient Greek concept of a fifth element, beyond earth, air, fire, and water. Unlike the static cosmological constant, quintessence would be a dynamic energy field. It could vary in strength and density across space and time. It could have been weak in the early universe, allowing galaxies to form, and only recently become dominant. Starting the acceleration we see today, this is a compelling idea because it opens up a range of possible futures for the cosmos that are far more dramatic than the steady, cold expansion of the lambda model. If quintessence is real, its future behavior is unknown. It could decay away, allowing gravity to reassert itself. It could strengthen, leading to a far more violent end. The fate of everything would depend on the properties of this invisible, ethereal field that we have only just begun to hypothesize. But to test these ideas, to move from phantom to physical reality, we cannot rely on supernova alone. We need new eyes. We need to see the universe in a whole new light. We have to become cartographers of the cosmos, not of the objects within it, but of the underlying structure of space and time itself. And to do that, we are building the largest and most precise maps of the universe ever conceived. The key to understanding dark energy is to measure its effects with excruciating precision over the entire history of the cosmos. We need a fossil record of expansion, and we have one dot. It's called the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, a faint, cold light that fills every cubic centimeter of the universe, a relic from a time 380,000 years after the birth of the cosmos, when it had cooled enough for atoms to form and light to travel freely. This light has been traveling for over 13 billion years, and it carries an imprint of the infant universe. By studying tiny, microscopic fluctuations in the temperature of this background radiation, patterns of hotter and colder spots, we can discern the fundamental parameters of the universe, its age, its composition, and its geometry. Space-based observatories like NASA's WMAP and the European Space Agency's Planck satellite have mapped this fossil light in stunning detail. The patterns they see are a perfect match for a universe dominated by dark energy and dark matter. The size and distribution of these hot and cold spots are a direct probe of the universe's expansion history, confirming the presence and strength of the accelerating force. But the CMB is just the beginning. The next frontier is baryon acoustic oscillations, or BODOT, in the early universe. Before the CMB was released, it was a searing hot plasma of particles and light. Gravity tried to pull matter together into clumps, while the intense pressure of the radiation tried to push it apart. This created massive, spherical sound waves that rippled through the primordial soup. When the CMB was released, these waves froze in place, leaving a characteristic signature preferred scale, like a cosmic ruler etched into the fabric of the universe. This ruler is about 500 million light-years long today. By looking at the large-scale distribution of galaxies, we can see the ghost of these sound waves. Galaxies have a slight statistical preference to be separated by this specific Distance, the frozen echo of those primordial sound waves. By measuring this standard ruler at different cosmic epochs, looking at nearby galaxies and galaxies billions of light years away, we can track how the expansion rate of the universe has changed over time. It's a direct, robust way to measure the work of dark energy. To do this on a colossal scale, we have projects like the Dark Energy Spectroscopic Instrument, or DESI, mounted on a telescope in Arizona. DESI is a robotic array of 5,000 tiny, precise fiber optic eyes. Its mission is to capture the spectra of tens of millions of galaxies and quasars, building a 3D map of the universe stretching back 11 billion years. It is, in essence, taking a cosmic CT scan, and the patient is space-time itself. By tracing the BAO imprint through this vast volume, DESI will provide the most stringent tests yet for our models of dark energy. Is it a constant cosmological constant? Or is it a dynamic quintessence, changing over the eons? The data is pouring in, and the early results are already hinting that the story might not be as simple as we thought. There are subtle tensions, whispers in the data that suggest the density of dark energy may not be perfectly constant. We are on the verge of knowing, but knowing the nature of the phantom is one thing. Accepting what it intends to do is another, because if dark energy behaves in certain ways, the future it paints for the cosmos is not just cold and dark, it is actively violent. Let us assume, for a moment, that the phantom is not a benign, constant force. Let us imagine that the quintessence models are correct, and that dark energy strengthens over time. What future does this paint? It leads to a scenario so terrifying it has been given a name that needs no explanation: the Big Rip dot in our current universe. Dark energy's repulsive force is dominant on the very largest scales, the gaps between galaxy clusters. But on smaller scales, gravity is still king. The gravitational glue holding a galaxy, a solar system, or an atom together is far stronger than the expansive pull of dark energy in that local region. But in the Big Rip scenario, this changes. The density of dark energy doesn't just remain constant. It increases. It grows without bound. The phantom becomes a monster. The first thing to go would be the cosmic web, the delicate filamentary structures that connect clusters of galaxies would be stretched and severed. The great attractor would lose its grip on us. Our Milky Way would find itself truly alone. Its journey towards the attractor suddenly and violently canceled. Then, as the force grows stronger, it would begin to attack smaller structures. The gravitational bonds holding our local group of galaxies together would be overwhelmed. The merger with Andromeda, once our cosmic destiny, would be called off. The space between our galaxies would expand so rapidly that they would be flung apart, their gravity no longer able to bridge the gap. But the horror is just beginning. Next, the phantom would set its sights on individual galaxies. The Milky Way itself would be torn asunder. The stars that have orbited our galactic core for billions of years would be ripped from their orbits, flung out into the ever-accelerating void. The galaxy would be shredded. Then it would come for our solar system. The sun's gravitational hold on Earth, on Jupiter, on every planet would be broken. We would be flung away from our life-giving star, a frozen, lonely rock on an endless, accelerating journey to nowhere. And it would not stop there. The phantom's force would now exceed the strength of the bonds that hold matter together. As the acceleration intensifies, it would attack the Earth itself. The planet would be torn apart. Mountains would fly into space. The very rocks would disintegrate then. It would come for you. Before the final moment, you would witness the air around you flying away. The molecules of the atmosphere would be ripped apart. The forces holding your body together would be overcome. Your atoms would be torn from one another. In the last fleeting instants, even the atoms themselves would be shredded. Atomic nuclei would be torn apart into protons and neutrons. The protons and neutrons would be ripped into quarks. Every single piece of matter, every fundamental particle, would be isolated from every other by an ever-widening gulf of space, expanding so fast that no force in the universe could ever bring them together again. The universe would end not with a crunch or a freeze, but with a screama, silent, instantaneous dissolution of space-time itself into a causally disconnected mist of lonely particles. The Big Rip is the most violent end conceivable. It is the ultimate victory of the phantom over every other force in nature. Thankfully, this is a speculative model, and most data currently points towards a constant dark energy, which would spare us this grisly fate. But the fact that our equations even allow for such a possibility tells us what a powerful and terrifying beast we are dealing with. The phantom is real. It is accelerating the universe. And while it may not rip us apart, its ultimate victory is still assured. For even in its most gentle form, its implications are profound. It dictates that the universe of the future will be a lonely, isolated, and dark place. The galaxies beyond our local group will one day be pushed so far away, so fast, that their light will never again reach us. The cosmic horizon will shrink. The evidence for the Big Bang, the CMB, will fade away. Future cosmologists, born on a world in the far future, will look up at an empty, static sky and have no clue that there was ever a beginning, or that there are other islands in the cosmos. The phantom is erasing the history of the universe and sealing its fate. We have found the engine of the cosmos. We have measured its power. We are beginning to map its influence. We have given it a name, but in doing so, we have uncovered a mystery far deeper than the one we started with. We have traded the simple, comforting pull of gravity for the silent, terrifying push of a vacuum that is anything but empty. We now know the force that is guiding the journey of everything. But this knowledge forces upon us one final, unsettling question. A question that takes us beyond the physics of the known and into the realm of the ultimate. If dark energy is truly the dominant force in the universe, if it is destined to create a future of infinite, empty, cold, and lonely space, then why does the universe have such a force woven into its very fabric? What is the purpose of a phantom? We have met the phantom. We have felt its push, a force born from the vacuum itself. It is shaping the destiny of all things, stretching the cosmos towards a cold or a violent end. But there is a problem with this picture, a glaring contradiction. If dark energy is the emperor, the supreme force driving the expansion of the universe, then why are we falling? We are not simply drifting apart on the cosmic tide. We are not passive raisins in an expanding loaf. We are being pulled with purpose, with direction. Our Milky Way galaxy, along with our entire local group, is moving at a staggering 600 kilometers per second towards a specific point in the sky, a region veiled by the bulk of our own galaxy. We are rushing towards the great ATTRACTOR. This is not the gentle, uniform flow of expansion. This is a raging river within that flow, a cosmic current so powerful it bends the paths of thousands of galaxies. This is a paradox. How can the universe be flying apart on the largest scales, while on this immense but local scale, we are being dragged together? The answer lies in the shadows. It forces us to admit that most of the universe is not just dark energy. It is also dark, invisible, unseeable. We have been mapping the cosmos using light, but light is a liar. It shows us only a sliver of reality. To find the source of the great pull, to understand the true architecture of our cosmic home and the nature of this mysterious current we are caught in, we must learn to see without light. We must become detectives of the invisible. We must map the cosmos in the dark. Let's return to that fundamental question. What is pulling us? For decades, the Great Attractor was a name for our ignorance. We knew it was there because we could feel its gravitational tug. But when we looked in its direction, we saw almost nothing. It lay directly behind the central bulge of our Milky Way, in a region astronomers call the zone of avoidance. Imagine trying to see a distant city through a dense, brilliant fog. That was our predicament. The zone of avoidance is a swath of sky obscured by the gas, dust, and countless stars of our galaxy's galactic plane. Invisible light, it is a wall, a blind spot in our cosmic vision. But we are a stubborn species. If we cannot see with our eyes, we will see with our minds. We will build new eyes. Our first breakthrough came not from optical telescopes, but from instruments that could peer through the cosmic fog. We turned to radio waves and X-rays. Radio telescopes can detect the faint or natural emission from neutral hydrogen gas at a wavelength of 21 centimeters. This signal slips through the interstellar dust that blocks visible light. By mapping this hydrogen, we could begin to trace the structures of galaxies hidden behind the zone of avoidance. Then came X-ray astronomy. Galaxy clusters, the largest gravitationally bound structures in the universe, are not just collections of stars. They are filled with incredibly hot, tenuous gas, so hot it glows, not in light, but in X. This multi-million-degree plasma is a beacon, revealing the presence of immense gravitational potential wells. Satellites like Rosetta and later XMM Newton and Chandra pointed their X-ray eyes towards the Great Attractor, and what they saw was breathtaking. There wasn't a single monolithic object. There was a sprawling metropolis of galaxies, a vast confluence of matter. They found the Norma cluster, a massive cluster of galaxies, about 220 million light-years away, sitting right at the heart of the gravitational anomaly. But the Norma cluster was just the downtown core. It was part of a much larger structure, a sprawling supercluster of galaxies. We had found the source of the pull, but in finding it, we realized the Great Attractor was not nearly strong enough. The mass of all those galaxies, even combined, was insufficient to account for the immense velocity of our motion, the motion of not just our local group, but of thousands of other galaxies in our vicinity, all streaming in the same direction. There was more mass there than we could see, a lot more this was not a new problem. In fact, it was a ghost that had been haunting astronomy for almost a century. The ghost of missing mass. The story begins in the 1930s with a brilliant, uncompromising Swiss astronomer named Fritz Zwicky. He was studying the Coma Cluster, a vast collection of thousands of galaxies. He measured the velocities of the galaxies orbiting the cluster's center. What he found was shocking. The galaxies were moving far too quickly. According to the laws of gravity, the cluster should have flown apart long ago. There was simply not enough visible matter stars, gas, dust hold it together with such fierce gravity. Zwicky concluded there must be some form of dunkelmaterial dark matter providing the extra gravitational glue. His colleagues largely dismissed him. He was ahead of his time. The case was solidified in the 1970s by astronomer Vera Rubin. She was meticulously measuring the rotation curves of spiral galaxies, how fast stars and gas orbit at different distances from the galactic center. According to Newtonian gravity, stars on the outer edges of a galaxy, far from the central mass, should orbit much more slowly, like Pluto in our solar system compared to Mercury. But Rubin found something different. The stars on the outskirts of galaxies were orbiting just as fast as those near the center. The only explanation was that galaxies were embedded in enormous, massive halos of something invisible, something that did not emit or absorb light, but whose gravity dominated the galaxy's structure. Dark matter. We now know that dark matter makes up about 27% of the universe, over 5 times the amount of normal matter. It is the unseen skeleton upon which the visible universe is built. It forms the gravitational wells that collected the first gas, leading to the birth of the first stars and galaxies. Without dark matter, our universe would be a formless, dim haze. There would be no us. And it is the gravitational pull of dark matter, the vast, hidden concentrations of it within the great attractor region, that is the true source of the cosmic current we are caught in. But the story doesn't end there. Finding the great attractor was like finding a massive mountain range. It explained why the rivers were flowing towards it. But we soon discovered that our cosmic river was part of a watershed on an unimaginable scale. We had to zoom out, further than we ever had before. We are now standing at the precipice of the future, looking out across an ocean of time so vast that the entire history of our cosmos up to this point is merely the first grain of sand on an endless beach. That this is not just a forecast. This is a eulogy for the future, a travel guide to the end of everything. This is the final chapter, the story of the last light. Let us begin our journey into the deep future with the most likely, the most gentle, and in many ways, the most terrifying of all endings, the Big Freeze. This is the future dictated by a constant dark energy, a cosmological constant that simply persists, unchanging, forever. The timeline we are about to explore is not science fiction. It is a direct extrapolation of the laws of physics as we understand them today. It is the universe's current resume projecting itself forward into eternity. We live in the golden age of the universe, the stelliferous era, the time of stars. Right now, the cosmos is brimming with light and energy. New stars are igniting in great nebulous clouds. Galaxies, like our Milky Way, are vibrant, dynamic cities of suns. But this will not last in about 4 to 5 billion years. our Milky Way will begin its long foretold merger with Andromeda. It will be a slow, majestic ballet, a billion-year-long gravitational waltz. Stars will be flung into new orbits, but very few will actually collide. The two great spirals will coalesce into a single, giant, elliptical galaxy. Our Sun, now a red giant, will have long since incinerated the inner planets, but it may well survive, tossed into a new orbit in this hybrid galaxy. For trillions of years, the universe will still be a bright place. The longest-lived stars are the red dwarfs, small, cool, and incredibly frugal with their nuclear fuel. They can shine for tens of trillions of years. The night sky from a planet orbiting a red dwarf in the Milky galaxy will still be filled with the faint, ruddy glows of its stellar neighbors. But star formation is already peaking. Galaxies are running out of the cold, dense gas required to birth new stars. One by one, the great stellar nurseries will fall silent. In about 100 trillion years, the last star will be born. The stelliferous era will officially end. The universe enters a long, slow twilight. This is the degenerate era, the era of stellar corpses. The sky will grow dark. The dominant objects will no longer be shining stars, but their remains, white dwarfs, neutron stars, and black holes. White dwarfs, the Earth-sized embers of sun-like stars, will slowly cool over eons, fading from white to yellow to red, and finally to black. They will become black dwarfs, cold, dense spheres of crystallized carbon and oxygen, drifting in the darkness. Occasionally, the silence will be broken. A chance gravitational encounter between two brown dwarfs might briefly ignite a new, faint star. A white dwarf might steal enough mass from a companion to explode as a final, forlorn supernova. But these will be rare, flickering candles in an ever-expanding vault of black dot. The galaxies themselves will be changing. As the universe continues to expand, accelerated by dark energy, a great isolation will set in. First, the distant galaxy clusters will vanish over our cosmic horizon. Their light no longer able to overcome the ever-increasing expansion rate. Then, the galaxies within our local group will be the only ones left, bound together by gravity. But even this bond will be tested over unimaginable timescales. Gravitational interactions between the degenerate stars and black holes will slowly evaporate the galaxies. Stars will be flung out into the intergalactic void, one by one, like sparks from a dying fire. The great structure of Milky will dissolve. Now, only the black holes remain as the last significant structures. They will be the kings of a dead universe. They will slowly, imperceptibly, grow by accreting the occasional wandering black dwarf or packet of dark matter. But their reign is not eternal. In the 1970s, Stephen Hawking made a discovery that sealed the fate of even these titans. Quantum mechanics dictates that space is not empty. It is a seething foam of virtual particles. At the very edge of a black hole's event horizon, one of these virtual particles can fall in while its partner escapes. This process, Hawking radiation, causes the black hole to slowly lose mass. It evaporates. It begins slowly. A black hole with the mass of our Sun would take 1,067 years to evaporate. That is a 1 followed by 67 zeros. The number is so large, it has no name. The supermassive black hole at the heart of Andromeda, millions of times more massive, would take around 10,100 years. But in a universe with an infinite future, even these numbers are just a phase. One by one, in a final flash of gamma radiation, every black hole will vanish. What remains? Almost nothing. The universe is now an inconceivably vast, expanding, and Xinhu perfectly empty void. The temperature everywhere approaches absolute zero. The only particles left will be photons, neutrinos, electrons, and positrons, all so spread out that they may never interact again. If protons, the very building blocks of atomic nuclei, are unstable in some grand unified theories suggest they are, then even the ghosts of atoms will decay, dissolving into radiation in about YP years. The universe will be a thin, cold, ultra-diffused soup of subatomic particles and radiation, forever diluted by an expansion that never ceases. This is the big freeze, the heat death of the universe. Not an explosion, not an implosion, but a slow, silent, and irreversible fading of all energy, all structure, all complexity, and all light into a state of maximum entropy, a state of perfect, eternal equilibrium. The story is over. Nothing happens, and nothing will ever happen again. It is the ultimate silence. In this scenario, dark energy is not a constant, but a form of quintessence that strengthens over time. Its density increases, and its repulsive force becomes more and more powerful. The end does not come in quadrillions of years. It comes in a finite time, perhaps 22 billion years from now. The acceleration does not just move galaxies apart. It begins to overwhelm all other forces. First, the cosmic web is shredded. Then, galaxy clusters are torn apart. Then, individual galaxies, the gravitational bonds holding Andromeda together, are shattered before it even fully forms. The horror accelerates. As the phantom's force intensifies, it attacks smaller and smaller structures. A billion years before the end, solar systems are ripped apart. Planets are flung away from their stars. In the final moments, the force exceeds the nuclear strong force that holds atomic nuclei together. Planets, rocks, your own body are explosively disassembled. Molecules, atoms, nuclei, protons, neutrons, all are torn into a mist of fundamental particles, isolated from one another by an expansion so violent that no force in the universe can ever bring them back together. The universe ends in a single, instantaneous moment of catastrophic disintegration, a final, silent scream. What if the phantom weakens? What if dark energy decays away or reverses its nature, becoming an attractive force? Then, gravity could stage a comeback. After tens of billions of years of expansion, the universe would reach a maximum size, pause, and then begin to contract, slowly at first, then faster. The redshift of galaxies would turn into a blue. The cosmic microwave background, the relic heat of the Big Bang, would begin to warm. The night sky would grow brighter, not with new stars, but with the gathered light of the entire universe, compressed as the contraction accelerates. The large-scale structure of the cosmos is crushed. Galaxy clusters merge violently, then galaxies. The temperature soars. Stars are evaporated by the intense background radiation. In the final minutes, the universe becomes a single hot soup of particles. Atoms are torn apart. Atomic nuclei dissolve into a quark-gluon plasma. The conditions of the Big Bang are recreated. The universe ends where it began, a singularity, a point of infinite density and temperature. But does the story end there? Some theories, like conformal cyclical cosmology, suggest that a big crunch could seamlessly trigger a new Big Bang. The universe dies and is reborn from its own ashes in an endless cycle of expansion and contraction of Phoenix universe. In 2014, a team of astronomers, led by R. Brent Tully from the University of Hawaii, announced a discovery that redefined our cosmic address. They had used new techniques to map the velocities of thousands of galaxies in our local universe, tracing the flows not just towards the great, but across hundreds of millions of light years. What they revealed was our true home, not the Milky Way, not the local group, not even the Virgo cluster. They revealed a structure of such immense proportions that it dwarfs all of them. They named it Laniakea dot. It is a Hawaiian word meaning immeasurable heaven, and it is a fitting name. The Laniakea supercluster is our cosmic continent. It is a vast filamentary network of over 100,000 galaxies, stretching across 520 million light-years of space. Our Milky Way is not even a dot on this map. We are a single grain of sand on its shore within Laniakea. Galaxies flow along great gravitational tributaries, like rivers flowing down a mountain valley, all eventually converging towards the great attractor, which acts as the gravitational center or the great basin of our supercluster. We are not falling towards the great attractor as an isolated target. We are part of a vast continental scale flow of galaxies, all streaming towards the same gravitational valley. This is the solution to the paradox. Dark energy dominates the global expansion of the universe, the space between superclusters. But on the scale of Laniakea, the local gravity of all that dark matter, the collective pull of 100,000 galaxies and their immense, invisible halos is still king. It creates a local current so strong that, for now, it overpowers the phantom's push. We are like a fish in a powerful river, being carried along by the current, while the entire ocean beyond the river's mouth is rising, threatening one day to swallow the river whole. But as the team mapped Laniakea, they noticed something else, something that completed the picture of our motion. To understand why a river flows so swiftly, you must look not only at what is pulling it downhill, but also at what is not holding it back. They found that behind us, in the opposite direction of the great attractor, there is nothing, or as close to nothing as the universe gets, a vast, empty void, a region of space remarkably devoid of galaxies and, therefore, of dark matter. They called it the dipole repeller. The concept is brilliant. You are not just being pulled from the front, you are also being pushed from the back, but not by a force, by a lack of one. Imagine you are in a crowded room and everyone is pressed together. Then a door opens on the far side and people begin to stream through it. You are not being pushed. You are simply able to move into the newly emptied space. Now, imagine that the crowd behind you suddenly vanishes. The pressure at your back is gone, and you are free to move forward more easily into the space where the crowd is pulling you. The dipole repeller is that empty space. It is a cosmic void, of such profound emptiness that it offers no gravitational pull to hold us back. The combined effect of the great attractor's pull from the front and the dipole repeller's lack of pull from the back is what creates our full observed velocity. Our motion is not a simple fall. It is a slide down a gravitational hill with a steep drop ahead of us and no slope behind us to climb. We now have a near complete picture. We know our local cosmic address. We are on the outskirts of the Laniakea supercluster, sliding down a gravitational filament towards the great attractor. Aided by the emptiness of the dipole repeller behind us, we have mapped the invisible. We have found the source of the pull. But this grand discovery, this understanding of our place within a cosmic continent, leads to a question that is even more dizzying. A question that takes us to the very limit of what we can observe and what we can possibly know. Laniakea is moving. Our entire cosmic continent, all 100,000 galaxies, is drifting. It is being pulled by something even larger, even more massive, something beyond what lies beyond Laniakea. What is powerful enough to pull an entire supercluster? When we zoom out beyond Laniakea, the universe reveals its true structure, the cosmic web. This is the largest pattern in nature, a vast, interconnected network of galaxies strung along filaments of dark matter, like pearls on a string. These filaments stretch for billions of light years, connecting superclusters in a delicate lacework. Between them lie the great cosmic voids, the voids, bubbles of near emptiness, like the dipole repeller, but on a scale that defies comprehension. Our Laniakea supercluster is just one node in this infinite web, and the web is not static. It is flowing. In the 1980s, astronomers discovered that not only are we moving towards the great attractor, but our entire local group, the Virgo cluster, and indeed the entirety of Laniakea, are all moving in the same direction relative to the uniform expansion of the universe. This grand, coordinated motion was dubbed the dark flow. It is as if a distant, unseen hand is tugging on the entire cosmic tapestry. The great attractor is just a weight. Laniakea is just a carriage in a much longer train. What could possibly exert such a pull? The gravitational influence of even a massive supercluster like Laniakea should only extend so far. The dark flow suggests a structure so immense, so massive, that its gravity can be felt across billions of light years. There are candidates. The Shapley supercluster, the largest concentration of matter in our local universe, lies about 650 million light-years away, beyond Laniakea. It is a staggering agglomeration of dozens of massive galaxy clusters. Its gravitational pull is undoubtedly contributing to our motion, perhaps even dominating the pull of the great attractor itself. We are likely flowing toward Shapley, but some cosmologists wonder if even Shapley is the end of the line. The dark flow seems so coherent, so unwavering, that some have proposed more exotic explanations. Could it be the gravitational influence of another universe in a vast multiverse, tugging on our own from outside the confines of our space-time? The idea is radical, almost heretical, but the data is persistent. We are hitting the limits of our observable universe. The cosmic horizon, the point from which light has had time to reach us since the Big Bang, is the ultimate wall. We cannot see what lies beyond it. But gravity, theoretically, does not respect that horizon. The mass distribution beyond our cosmic light cone in principle, be pulling on us. We are like sailors on a medieval ship who can feel a powerful current carrying them, but have no idea what continent lies over the horizon generating that current. We can only measure our drift and wonder. We have journeyed from the spin of our planet to the orbit of our sun, to the sail of our galaxy through the Milky Way, to the collision course with Andromeda, to the great current towards the great attractor, to the continental drift of Laniakea, and now to the dark flower motion of everything. We can see towards something we cannot, each time we think we have found the ultimate source of our motion. We find it is merely a local manifestation of a much larger, much more powerful drift, this relentless scaling up. This never-ending nesting doll of motion leads us to a final, terrifying, and sublime conclusion. There is no center. There is no stillness. There is only motion within motion within motion. We are on a ride within a ride within a ride, and we have only just begun to perceive the true scale of the amusement park. We have mapped the invisible matter that pulls us. We have traced the currents across the cosmic continent. We have felt the tug of structures beyond our vision. But all of this, the spinning, the orbiting, the colliding, the flowing is happening within a universe that is itself evolving, changing, and being shaped by the phantom force of dark energy. This brings us to the final, unifying question. The question that ties the push of the phantom to the pull of the architect. The question of time itself. We have asked where everything is going, but to truly understand the destination, we must ask a different question. We must ask when. When will the phantom finally overcome the architect? When will the expansion rip apart the very cosmic web we have just so painstakingly mapped? When does the journey end? The answer lies not in a place, but in a moment, a final moment, and to find it, we must journey to the end of time. All journeys have an end, even this one. We have mapped our path through the cosmos. We have felt the spin of our world, the pull of our star, the drift of our galaxy. We have been swept up in a cosmic current towards a hidden attractor and felt the phantom push of the vacuum itself, accelerating the expansion of everything. Asterisk, we have asked where we are going. We have traced the trajectories across the gulf of space, but space and time are inseparable. To know the true destination, we must now ask the most profound question of all. We must ask, when does the story of the universe conclude? Is it a sudden, violent finale, a slow, cold fading, or a cyclical rebirth? The answer is written in the nature of the phantom dark energy, its subtle, constant strength, or its potential for change, will dictate the final moment for every galaxy, every star, every planet, and every atom. It is a beautiful, hopeful idea, but the data we have today, the relentless acceleration we observe, makes it the least likely of our fates. The phantom shows no sign of relinquishing its throne, so we are left with the freeze, the long, slow goodnight, a future of near infinite time filled with almost nothing. This knowledge is the ultimate conclusion of our journey. We have traced our path through space only to find that it terminates in the absolute cold of deep time. But before we conclude, I must ask you to pull back, to return from this vista of ultimate endings, to return to here, to now, to this room, to you, because this story, for all its cosmic grandeur, is not really about the universe. It is about us. Think of everything we have done, We, a species born on a speck of dust, orbiting a mediocre star, in the quiet suburbs of a common galaxy, have done the impossible. We have measured the spin of our planet. We have calculated the orbit of our world. We have felt the motion of our sun. We have predicted the collision of our galaxy. We have traced the currents of our supercloud. We have discovered the acceleration of all of space, and we have predicted the end of time itself. We have done this with mathematics, with telescopes, with curiosity, with a relentless, burning need to understand our place in the cosmos, in a universe destined for cold, empty silence. We are the source of meaning. We are the universe becoming self-aware. We are the cosmos looking back at itself and asking, where am I going? The grandeur is not out there in the galaxies and the forces. The grandeur is in here, in the mind that can comprehend them. The journey of everything is a magnificent story, but it is a story that only has meaning because we are here to tell it, to witness it, to feel awe in the face of its immensity and humility in the face of our own fragility. We are temporary. Our planet, our sun, our galaxy, all are temporary. But in our brief, brilliant moment of consciousness, we have grasped the narrative of the cosmos. We have found the story of everything. So, where is everything in the universe going? It is going towards silence, towards cold, towards dark. But you are here, now, and in this moment, you are the one who has woken up, looked out the window, and understood the nature of the journey. You are the universe, thinking. You are the universe, feeling. You are the universe, wondering. And as long as that continues, as long as there is a single point of light and consciousness to observe it, to question it, to feel awe in its presence, the cosmos, in the only way that truly matters, is alive. The destination is fixed, but the journey is everything, silence and cold, and an end to all stories. That is the destination our physics has painted for us, a final, sobering answer to the great question of our journey. The last light winks out, and the cosmic clock ticks on towards an infinite, featureless forever. But what if we have been asking the wrong question? Where is everything in the universe going? Implies a journey within a container, a voyage from a starting point to a finishing line plotted on a map that already exists. We have traced this path with breathtaking precision, from our spinning planet to the heat death of everything. Yet, at the very edge of our understanding, a more radical, more bewildering possibility is emerging. What if the universe isn't just a single, self-contained entity on a one-way journey? What if the destination is not a place or a state, but a transformation? What if we are not just passengers on a bullet train, but cells in a vast cosmic body whose ultimate purpose we cannot even begin to fathom? To find an answer that transcends the freeze, the rip, and the crunch, we must be willing to step beyond the known laws of physics, into the realm where science bleeds into philosophy, and cosmology confronts the nature of reality itself. We must ask what lies beyond the map. Journey has been confined to a single, fundamental assumption that we live in a four-dimensional universe, governed by the laws of general relativity and the Standard Model. This framework is spectacularly successful. It brought us here to the edge of time, but it is also incomplete. It cannot explain the phantom dark energy. It cannot reconcile gravity with the quantum world. It is a magnificent map of a single continent, while whispers speak of entire other worlds across an ocean we cannot yet sail. The quest for a deeper answer, a theory of everything, has led physicists to propose realities that defy everyday intuition. For instance, suggests that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrations of these strings give rise to every particle and force we see. Much like different vibrations of a violin string create different notes. But for the math to work, string theory requires more than the 4 dimensions we experience. It requires 10 or even 26. These extra dimensions are curled up, compactified, on a scale a billion times smaller than an atom. Think of a garden hose. From a distance, it looks like a one-dimensional line, but an ant crawling on it knows it has a second dimension curled around its circumference. Our universe, according to this idea, might be like that hose. We are macroscopic creatures, blind to the tiny, curled-up dimensions that define the very fabric of reality. This isn't just an abstract concept. The properties of these extra dimensions would determine the fundamental constants of nature, the strength of gravity, the mass of an electron. In a sense, our universe's laws are not absolute. They are a local ordinance, determined by how its hidden geometry is folded. And if there are many ways for these dimensions to fold, then there could be many different universes. This is the multiverse. Not a single destination, but a frothing ocean of potential realities, each with its own unique set of physical laws. In this breathtaking scenario, our universe, with its specific balance that allows for galaxies, stars, planets, and life, is just one bubble in a vast cosmic foam. Some bubbles might have stronger gravity, collapsing instantly. Others might have no nuclear force, so atoms never form. In others, dark energy might be so powerful that the big rip happens in the first picosecond. We do not live in a fine-tuned universe. We live in a viable one. We are here because, in the infinite lottery of the multiverse, we drew a winning ticket. The where of our journey becomes less important than the why here. This concept offers a potential solution to the mystery of the phantom. The value of dark energy isn't a bizarre, fine-tuned accident. It is simply the value that ended up in our particular bubble. The cosmological constant problem isn't a problem. It's a selection effect. But if the multiverse is real, it changes the meaning of our journey entirely. The cosmic current we are in, the pull of the great attractor, the push of dark energy, is all local traffic. The ultimate going may not be towards a final state within our universe, but towards a deeper understanding of our address within a frothing, infinite meta-reality. There is another, even more mind-bending possibility, one that questions the nature of the map maker. The holographic principle suggests that our perception of a three-dimensional universe is an illusion. It proposes that all the information contained within a volume of space, every star, every planet, every person, can be encoded on a two-dimensional boundary that surrounds it. Like a cosmic DVD, our reality, with its rich depth and texture, would be a projection, a hologram, from this underlying two-dimensional information structure. The universe isn't just described by information, it is information. If this is true, then the journey of everything is not a physical journey through space and time, It is a computational process. The expansion of the universe, the formation of galaxies, the evolution of life, it could all be the output of a cosmic algorithm running on the surface of reality. Where is everything going? It is going where the code is leading. The big freeze is not the end of energy, but the end of meaningful computation. When the universe reaches maximum entropy, no more complex calculations can be run. The processor halts. This idea leads to a question that is both thrilling and terrifying. If our universe is a projection, what is the source? Are we part of a cosmic simulation? The question is not as frivolous as it seems. If it is possible for an advanced civilization to create a simulated universe, and if there are many such civilizations, then the number of simulated universes would vastly outnumber the one base reality. Statistically, we are more likely to be in a simulation than not in this scenario. Our journey, our fears, our questions about dark energy and the end of time, are they just part of the programmed narrative? Is the phantom a feature of the code? A scheduled end-of-program sequence? And finally, we must consider the most profound wildcard of all, consciousness. We have traced the journey of matter and energy, but we have neglected the journey of the observer, the one who is asking the question. Quantum mechanics has long grappled with the measurement problem. Why does a quantum particle exist in a blurry cloud of probabilities until it is observed, at which point it chooses a definite state? This has led to interpretations that inextricably link the consciousness of the observer with the reality that is observed. Radical conclusion is that the universe only takes on a definite form when it is measured by a conscious entity without a mind to perceive it. Reality remains in a state of potentia, a shimmering haze of maybes.